Yeah, all right, good day, everyone. Today we're going to be looking at structural elements or elements of solid makings and force equilibrium and some rules we use in solving statics and problems like the static equilibrium equation. So the first thing we're going to do for me is to ensure you subscribe to this channel and turn on your notification bell. Also, ensure you don't click any part of this video so that you get the full details, everything we're going to dash out in this section. So, before you go into structural mechanics, you must know the elements we use in making a structure. And this is not structure, it's just strength of materials. And we have done introduction to strengths, but today I just want to look at how to actually resolve forces that causes some strengths. So actually, before we go to that place, let's look at some structural elements we have. We have a structural element called beams, we have columns, we have slabs, we have troughs, and so on. Now, before you can something like put all these structural elements in place, that are what we call support, we use in placing them in where they ought to be in structures. So we have basically three types of supports in structural analysis. We have basically three types of supports. So we have number one, we have the roller support, and the symbol is like this. We have roller. Then let's say it's carrying a beam. So it's carrying a beam. Please ensure you know the definition of beams, column, slab, and so on. Column just like structural elements that do mainly carry compressive loadings. And we all know that a column, even in case you don't know, a column mainly carries compressive load, although it can also resist bending. Let's look at sometimes buckling of columns and all that. So this is a roller and this is a symbol. Now what's a roller? A roller is a support that has only one reaction, or that resists loading in just only one direction. You have just only one reaction to load it, or one resistance to load it. So we can only react or resist loading in the vertical direction. You have only the vertical reaction, which is arrow V. That's a roller. So a roller has just a vertical reaction, and this is simple. This is support we use in mechanics or in structural analysis that have just only the vertical reaction. Then we also have what we call the pin support, the pin PIN, the pin support. So the pin support has a symbol. The pin support has a symbol, and they also call it hinge actually. And let's say there's a beam on top. There's a beam on top. So a pin support is a support that has two reactions. It can react or resist loading in the vertical direction, and it can also resist loading in the horizontal direction. So if I ask you to draw the free body diagram of this now, how you draw it is just going to represent this what's it called? To represent this column, this beam with the line. Then the pin will show that it's just resisting the loading with using the vertical reaction and the horizontal reaction. Same thing as this. But we are not going to show the free body diagram now. This is just the free body diagram of that. But let's just show everything out. So this is the beam and this is the support. So this is pin support, and it has vertical reaction and horizontal reaction. Now we also have free body diagram. Free body diagram is just something like a drawing that shows the actual forces acting on the member. Just a drawing that shows the actual forces acting on the member. So that's just a free body diagram, like the one I just drew. The last one we have is called the fixed or built-in support. A fixed or built-in support. The symbols like this. This one called fixed support. That means this place is fixed. It can resist horizontal loadings, vertical loadings. It can also resist horizontal loadings, and it can resist what we call bending moments. It can also resist what we call bending moments. So a fixed support is a support that can resist loads in three ways. You resist the horizontal loadings, you resist vertical loadings, and you also resist bending. This cannot resist bending. A pin cannot resist bending. A ruler cannot resist bending. So the things that can resist bending. So please take note of that. There's also what we call force equilibrium and static equilibrium equations. The static equilibrium equation we have. What is static? Static is just branch of mechanism that this effect of forces on body at rest, at equilibrium. The body is not moving. So we have the equation of static equilibrium, called a static equilibrium equation, which shows that the sum of forces in the x direction must be equal to 0, the sum of forces in the y direction must be equal to 0, and the sum of moment about any point must also be equal to 0. These are the static equilibrium equation. So any problem these three equations cannot solve is called indeterminate problem. For a problem to be determinate, it must be able to be resolved using this static equilibrium equation. Indeterminate problems or indeterminate structures are structures that cannot be resolved using the static equilibrium equation. So how do we actually use this? We are going to look at it when we are doing the resolution of forces. You know, force is a vector. We are still going to come from vector. Like the first one I'm going to look at, let's say you have two forces acting at a point. How do you actually add the two forces together? So the first thing we are going to look at in resolving all these forces, looking for resultant force or total force acting at a point, is what we call the parallel law of forces. The parallel law of forces. Just as we have the parallel law of vectors, we also have what we call parallel law of forces. Although both of them are almost the same thing, but instead of us to just mention vectors in general, we are actually looking at forces now. So what is the parallel law of forces? Now you know that parallelogram is just like a rectangle, but they have two slight heights. So this is what we call the parallelogram. It's a parallelogram, and let's say we have to like this now. This law states that you can write it down if you wish. This law states that if two forces are represented, look at it. If this is a parallelogram, it shows that this and this are the same. This and this are the same. So we have two sides here. Although we have four sides, two of each sides are the same. So basically, the main actual side we have is just this. So this and this are the same thing. This and this are the same. So we have this side and this side. So if two forces are represented, the law states that if two forces are represented in magnitude and direction. Why in magnitude and direction? Because a force is also a vector quantity. A vector quantity is a quantity that has magnitude and it also has direction. So let's say it has magnitude and direction. So we have this one and this. Let's call this one F1. Let's call this one F2. So that's what we're going to have. We are going to give the direction of them. We are going between them. It's still very important. So they say if two forces are represented by the two adjacent sides of a parallelogram in magnitude and in direction, then the resultant force is drawn from the point of intersection of these two adjacent sides in magnitude and in direction. The resultant force is drawn from the point of intersection. When this and this intersect, look at it here, and they also intersected here. So the resultant is drawn from here to this place. As far as both of them, they are moving in the same direction. So it's leaving, so it's also leaving. So if you want to, this is the resultant force in magnitude as well as direction. So this is the actual thing I'm looking for in this place. So if I have to ask you any question here, it's going to ask you, what is the resultant force? And sometimes you can also give the resultant to say what would be the value of the first force or the second force. So this angle, if this angle is theta, this one will be 180 minus theta from geometry. So let's say this one is F, this and this are the same, F1, this one is F2. So let's say if we call this angle beta and we call this one alpha. So they can also ask you what angle does the F1 makes with the resultant? What angle is the F2 making with the resultant? They can also ask you those questions. So how do you solve that? You want to solve those angles. You can also remember the sign rule for oblique triangles. You know how we call oblique triangles? Which are triangles that are not right-angled triangles. So any angle that is not a right-angled triangle, we call them oblique triangle. So it's just like this. Look at this. Look at what we have here. This is the resultant, and these are the two sides. So this is the first one, the second one. So you can see it. and so this one is 180 minus theta. This one is the resultant. And this one is the F1, this one is the F2, so this one is alpha, this one is beta. So if I ask you now, what's alpha, what's beta, what's F1, what's F2, you relate them using sine. What sine? The sine states that what is sine facing this 180 minus theta? So arrow over sine 180 minus theta must be equal to what is sine facing this beta? F1. F1 over sine beta, and it's also equal to what is sine facing this alpha? F2 over sine alpha. So arrow over sine of this must be equal to the F1 over the sine of this angle opposite to it. Then it will also be equal to the F2 over the sine of this angle opposite to it. So if you want to solve this equation, and you solve them in twos, just solve them. You solve the one that has no unknown and the one that has just one unknown, so that you'll be able to resolve it to get the answer. Now, what is the value of the resultant? Now, from this place, now they can also ask you what is the resultant. Like, you want to get the resultant from this parallel of forces. From this place, now the resultant will be equal to. Now, the first thing you do before I complete this, this is still the same thing as this, and this should be the same. It should be the same thing. So you complete it, then you use rules of trigonometry and others. So you're going to have arrow to be equal to the square root of f1 squared plus f2 squared plus 2f1 f2 cos of theta. That's what they're going to have. You have cos theta. That's what you have. Now, there are cases in which, please take note of this formula, is very important. There are some cases in which this plus will be minus. How can that plus be minus? Now remember that in vectors, vector, if you have like this, a vector, how do you represent vector? See, I'm going to do a class that is titled vectors. That is the title of the class. Vector. I'll show you what is a vector, types of vector quantities, how to present vector, rules of adding vectors. Rules of the parallel law of vectors is still one of the rules for adding two vectors together. To add the two vectors together. So remember, if you want to represent the vector with a straight line and an arrowhead. This line denotes the map just as the have like this now. As you can see, we have a straight line and an arrowhead. You must have a straight, not a straight, and you must have arrowhead. Now the line denotes the magnitude. If I call this one A and I call this one B, I'll call it vector AB. That's what I'm going to call it. And it is going from A to B, that's the direction. So if you have vector AB, it is same thing as minus BA. Vector AB is same thing as minus BA. Because the direction is now changing. So if this one wants to be minus, it's when these two, any of those two changes their direction. Let's say they were moving from A to B, they will now move from B to A. They will now move from B to A. They will now move from B to A. So let's look at this. If, let's say, for example, this guy is moving from this place to this place. Let's say this now changes the direction. Now we're going to have to like this. We're going to have to like this. We're going to have to like this. Then we also have this. They say this one is not changing the direction. This is F2. This is F1. So what will be the resultant? This one is theta. The resultant will be this. This will be the resultant. This one will be the resultant. So that resultant will be equal to the square root of F1 squared plus F2 squared plus 2. No, it will not be plus again. Why is it not plus? Because if this from here, if I consider AB, if I don't move it like BA, AB will not be equal to minus of BA. So that AB we used before will not be negative. Since it's not changing direction, so this one will not be minus 2F1 F2 cos theta. Why this one minus? Because one of these changes its direction. But if both of them are in the same directions, they are leaving, it will be plus. If one of them changes the direction, minus. If both of them are entering the starting point, will still be plus. So please take note of that. It's very important. So we are going to look at a typical example. I'll use this and this will solve the example so you know what we are trying to see. So let's look at the first example 1. Alright, example 1. You can write the question down. It goes like this. A pool of 5 kilonewtons. A pool of 5 kilonewtons and a push or a thrust of 2 kilonewtons are acting on a peg. what is the resultant force? What is the resultant force? And what is the direction of this resultant force to the positive x-axis? And what is the direction of this resultant force to the positive x-axis? To the positive x-axis. So let's try and see if we can run through this resultant force to run this question. So solution to the question. Solution. So the first thing we're going to do now, we're going to bring out only the force. Let's bring out only the force. I have the 5 kilonewtons, 5 kilonewtons. And so I have the 2 kilonewtons, the 2 kilonewtons. And the angle between them is what? 30. That's the angle between them. I tell you guys, the resultant automatically would be this. That will be the resultant. So this will be the resultant. Why? Because look at it. This is the starting point. One of them is coming into the starting point. The other one is leaving. Both of them, they are not going to the same towards the same direction. So if I want to calculate this resultant now, the resultant will be equal to the square root of f1 square plus f2 square minus, it's not plus. Why? Because one of them is entering the starting point, the other one is leaving. That's why it's minus. Minus 2f1, f2 cos of theta. And what is theta? Theta is the angle between them, and the angle between them is 30. When you start 30, this 30 there. So, what is the value of the first force? What is the value of the first force? The first one is 5 square. The second one is 2 square minus 2 times 5 times 2 cos, what is the angle between them? 30. So if we do this very well with your calculation calculator, all of time, if you do 5 square, that is 25, 4 square, that is 4. But go of time, let's run with our calculation calculator. We have the square root of 5 square plus 2 square minus 2 times 5 times 2 cos 30. Cos 30. So approximately our r here will be equal to, r here will be equal to, or r here will be equal to 3.42 kilonewton. Please take note, this line is not a straight line because it's just like a little slant line, something like this. That is a line, it's not a straight line, that resultant, it's not a straight line. If you take note of that, it's very important. Now, this is the first way to solve it. Now, the second way is to look. This is the answer to the question. So the second one is now, what is the direction? Like the second question is, what is this direction? This theta. What will be that theta? The direction of this result have to be positive x axis. What will be that direction? So I'm not going to solve the direction from here, although it might be very easy to solve the direction from here. And it could also be very hard. For example, now we can say, okay, let's solve the direction. We know that from here to here is 2, from here to here is 3.142, I mean 3.42. From here to here is 5. You can just use sine to calculate this and then remove it from 180 to see what you are going to have. But before we go there, we'll do that. Now let's assume both of them are leaving. For example, let's assume this one is coming out. Okay, let's just draw it again. Let's draw. We have our 5 kilonewtons here. Then we have our 2 kilonewtons this way, 2 kilonewtons. So let's assume this is the horizontal, this is horizon, line. Let's assume this one is just leaving the joint as well. So let's this one is leaving the joint. Let's the 2 is leaving the joint. So what will be this angle? And the line parallel to this will be this. That will be the line. So this line is parallel to this. The line parallel to this will be this other one. So this will be the resultant. That will be the resultant force. So will be the resultant force. For this, because both of them are in the same direction, this will be the resultant. Even though they are in opposite direction, the resultant force will be something that close the whole channel. So what is this angle? What is this angle? Now this angle, what is this angle here? This is this one. The angle of this 2 kilonewtons to the horizontal is 30. This one is 30. This will also be 30. It's also 30 degrees. That will be 30 degrees. This one is 30. This one will be 30. Then this other one, the angle of this upper one to the y-axis. That's what I'm trying to say. In case you cannot see that very well, what we have here is something like this. If this one is 30, it will also be 30 degree. It will also be 30 degree. Then this one should be 30 plus 30. Now the full angle, this full angle should be 90 because of quadrant. Angle of a quadrant is 90. So this the full angle should be 90. What will complete this to be 90? 30 as well. 30 plus 30 plus 30, that's 90. So this is also 30 degree. That's also 30 degree. Then this other one will be 90 as well. This one will be 90. It's 90 degrees. So the full angle will be what? So let's check what I do have. We have something like this. We have this. We have this. And we have this. We have this. And we have this. So these are our resultants. So the angle will now be 30 plus 30 plus 90. Let me draw so that it will be very big. We have something like this. We have this. We have this. Then we are having something like this. I just want to show that the thing is making sense. Or something like this. So then this will be, if I don't have that, this will be the resultant. So for that will be 30 plus 30, that is 60 plus 90, that is 150 degree. That's 150 degree. This one is 5 kilonewtons, this one is 2 kilonewtons. So if you check now, both of them they are leaving the starting point. So our arrow will now be square root of f1 square plus f2 square plus 2 f1 f2 cos 10. That is cos what now? What the angle between this and this? 150. That is theta. So what I will have will be arrow will be equal to the square root of 5 square plus 2 square plus 2 times 5 times 2 cos 150. So let's try this and see what I do have. Let's try that with the calculator. Cos 150, that is 5 square plus 2 square plus 2 times 5 times 2 cos 150. And the answer is still 3.42 kilonewtons. The same thing as this. So you can see the model is absolutely correct. It's absolutely correct. Then now let's check for the angle. Let's check for the angle between these. Okay, let's do it. Either you do this, either you do it from here, or you do it from here. Anyone is possible. So let's check for the angle between this resultant, and the positive x-axis. So look at it. You have this. Then remember that this 5 newtons is making an angle of 60 to the resultant. So from here is 60 degrees. Then from here to here to the what? Let's call it alpha. So the angle between this resultant and the positive angle is 60 plus alpha. So this alpha, we don't know it. We don't know alpha. So what is this angle? We don't also know that angle. So let's bring out that angle. That angle should be, look at this. Let's get the angle from here. This angle is alternate to this. So what is the angle between 2 and 5? The angle between 2 and 5 is 30. So this one is 30 degrees. This one also be 30 degrees. So this will be 30 degrees for looking at it. Not this other two. This other two. So this angle from here to here is alternate to this. That's what we have here. So that is 30. So what we have is something like this. You have something like this. We are having this. So this 30 degree is alpha. So our arrow is 3.42 kilonewtons. Then this, what is this y? That is 5. That is 5 kilonewtons. I don't put 5. So I'll put it, don't forget about the unity. Let's put 5. You don't need the unit now. Then this other one, this top one. So this is 2. This is 2. That is 2 kilonewtons. That's 2 kilonewtons. So from sine, we are going to need this 2 and this. So we are having sine. Okay, let's use the actual value for the first sine. So we are going to be having an arrow over sine of the angle facing arrow. That's sine 30. Let's just do it straight from law of time. That is 3.42 over sine 30 is equals to 2 over sine alpha. 2 over sine alpha. So if you cross multiply, we will be having sine alpha will be equal to 2 sine 30 over 2 sine 30 over 3.42. 2 sine 30 by 2 So let's try that. So sine alpha will be equal to what? That will be 2 sine 30 divided by 3.42. That is 0.2924. So alpha will not be the sine inverse of this other side, the arc sine of this other side, 0.42. That is 2924. If you do that, that will have what is sine inverse, shift sine of 0.2924. So what I will have, this week I'm having 17 degrees. That's what I'm having. I'm having 17 degrees. So what will be the value? What will be the value of our angle between the resultant and the positive x-axis? The angle between the resultant, that is from here to here. So let's call the angle beta. So the angle between the resultant and the positive x-axis, let's call it beta. So our beta would not be equal to alpha plus 60 is 17 plus 60. That's 7. So we are having 77 degrees. That is the angle between the resultant and the positive x. Now, we want to look at resolution of forces. Now we have just looked at how to solve problem using parallel law. Another law we can use for resolving forces is resolution of forces. Now, parallel law or resolution of forces was to give the same answer. So what we are going to do now, we're going to explain how to use the resolution of forces. Then we'll solve the question we solved before from that parallel law to see what we are going to have actually. It will be the same thing. Now, how do you use the resolution of forces? Resolution of forces is the act of splitting forces into its components. The act of splitting forces into its components. And what is the meaning of component of a force? Is the amount of a force going to a particular direction. For a plane, Cartesian coordinate of this nature, in plane, we have just two components, the x and y component. So we have a force acting in the x and y plane, as you can see it, with the first leg. So how do we find the component of this force in the x side and the y side? So what I'm going to do for me is to do that in the right hand side x is positive, the left hand side x is negative, the down side y is negative, the upper side y is positive. So if I say what is s component of this force, the s component should be, what I'm going to do for me is the summation of all the forces in the x direction at f equilibrium should be 0. So if you sum up all the forces, if it's at f equilibrium should be 0. So the sum of all the forces in the x direction now will be equal to the force times the cos of the angle between the force and the positive and the x-axis. Not just positive x-axis, just x-axis. This angle is it between f and x? Yes, so it's cos theta. So that's how you find the component of the force. Now the other thing I'm going to check is to check. Now this f is equal to the positive s or negative s to the positive s. So it should be positive, and you need to apply cos of this angle between f and the x axis. So that's how we find the s component. You can also do it this way, although we don't have to waste time. So if you use SOHCAHTOA here, this will be the opposite, and this will be the adjacent, and f is the hypotenuse. So if you want to relate opposite and hypotenuse, that is sine of this angle will be opposite to the hypotenuse. If you want to relate adjacent and hypotenuse, that will be cos. That is x and f is having cos. So that's running from there. But without wasting time, that's what if you want to resolve force to the x direction and the angle between the force and the horizontal direction or horizontal axis, what you do is just multiply the force by the cos of the angle between that f and the horizontal, not the vertical. You take note of that. So the y component of this force, the y component will be summation of all the forces in the y will be equal to summation of all the forces in the y should be equal to, if you want to check, is it upper or down? So the upper side is still positive. F now sine of this same angle between the force and the x-axis, this theta. This is how you find the component of the force. Then, what is the resultant force? The resultant will be the square root of the x component, square it, plus the y component, then you square it. That will be the resultant force. Then, first of all, what is the direction of the resultant? You have to draw it out to get the actual direction. You can ask what is the direction between the resultant and the positive x-axis or the negative x-axis. So that's why you have to draw it out before you get the result. Though the major way you solve it is that the direction will be theta is equal to tan inverse of sigma of x, that is s component over y, and f component over the x component, the y component over the s component. You just theta is equal to the tan inverse of the y component over the s component. That's how they normally do it. So, okay, let me just say on it. The theta will now equal to the tan inverse of the y component over the s component. So that's how they normally do it. So it's not in most cases this will work. You can solve it and still apply some rules of geometry to get the actual direction from the resultant. So note that this only work if the force is acting in where both x component and y component are positive. If it's here, that formula may not work. If you are looking for the direction to the positive x and it will not work, you have to also apply some extra way to run the stuff. So let's look at the question we solved before. Then let's resolve it using result forces. We're having a peg, we're having a force of 5 kilonewtons, we're having another force of 2 kilonewtons, and this one is 30, it's also 30. So let's also look for the resultant now. Let's look for the resultant of this force, 30 degrees. So that's 2 kilonewtons. So if you want to use the relational forces way to run this, the first you do, before complete this, found cardinal point, then you are going to bring this backward to actually show. Remember this was going to this side. So remember that. Actually, where it's going to, so it's going to the downside. It's not going to the upper side. So it's going to the upper side. So that's already there. So if you want to draw it very well, I'm going to draw it this way. I'm going to draw it this way. And this is going to this side. And this other one is going to this other side. So this is 2 kilonewtons because it's coming down. That is coming down. That's why this one is coming down. And the 5 is going up. And this one is going up. What is the angle between this and this? This 30 plus 30 is 60. This angle is alternating to this. This one is also 30. But this is alternating to this. That's 30 degrees. So this one is 2. This one is 5 kilonewtons. So let's check if we get this answer. So this one is very short to solve. It's not as hard as that. So let's check the S component. The S component will be 5 cos 60 because 5 is in the right hand side, but 2 is in the left hand side will be minus 2. Because if it's in the left hand side, S will be negative. So it will now be minus 2 cos 30. That's the angle between 2 and the S axis. If you solve this one, we're going to have answer. Let's see what we're going to have. We have 5 cos 60 minus 2 cos 30. So I'm having to put decimal place. I'm having 0.77 kilonewtons. That's what I'm having here. So the other one for the y side, the y component. For the y component, we have all the forces in the y direction will be equal to 5 sine 60 because 5 is in the upper side for y. For y, upper side is positive. Then the downside is still negative for y. Minus 2 sine 30. Although some people do use quadrant to look at the direction, but what I use is just check the cardinal point where x is positive, where x is negative, where y is positive, and where y is negative. So let's on this 5 sine, we have 5 sine 60 minus 2 sine 30 minus 2 sine 30. So 5 sine 60 minus 2 sine 30. So I'm having 0.33 kilonewtons. So we said the resultant force. Actually, look at what we are going to have. Let me show you how they got that resultant. What we are going to have, we're having y still positive. That means still going up, and it was 3 point. Let me draw it here. 3.33 kilonewtons, and s is still positive. You see, go to this side. We have, although it's very small, this one is just drawing. We have 0.77 kilonewtons. So if you complete this will be our resultant. And this will be the direction between the resultant and the positive x axis. So Please remember the answer we got from the resultant we saw before for the resultant and the angle of the resultant between the positive answer and the resultant. Please remember it because we are going to check whether they are the same thing. This is resultant. Our resultant will be the same is this square root of x squared plus y squared. So if you do this, what are you going to have? If you do this, you are going to be having 0.77 squared plus 0.33 squared. 0.33. Okay, that's 3.33, not 0.33. So it's still 3.42 kilonewtons. That's what I'm still having here. That's 3.42 kilonewtons. Now let's check the direction. Check the direction. The theta will now be equal to the tan inverse of y 3.33 all over x 0.77. So let's check what I'm going to have here. So we have the shifts tan inverse of 3.33 divided by 0.77. So what I'm having is 76.89. That's approximately 77 degrees. That's what I'm having. So our result is still 3.42. Then the direction is 77 degrees. As you can see, this is the same thing we also saw before, but different methods. This is how to use the forces to run the resultant force, or resultant of two forces, and the first one we did was how to use the parallel of forces to run it. So both of them works wonders, but parallel of forces only works for at most two forces, at least two forces. So if you have two forces, you have two forces. If you have one force, you might manipulate. But if you have more than two forces, I should make sure that there are two. The first one will be two for that to work. This works whether the force is 1, 2, 3, and above. This works for any number of forces. This works, but parallel will work for two forces. That's why they say if two forces are represented, that's why you make sure it's two forces. So thank you for today. God bless you. I'll see you guys in our next class.